This is Pat Kaplo. I'm reading problem number 2 on page 98 in chapter 4, a net force of 265 newtons. I like the way this problem begins because they explicitly say that the net force is 265 newtons. They're not using generic terms like a force, but specifically the leftover force of 265 newtons accelerates a bike and a rider at 2.3 meters per second per second. These are units and information that you're used to seeing from previous chapters, acceleration in meters per second squared. So we have the net force and the acceleration. What is the mass of the bike and the rider together? This is an application of Newton's second law. Newton's second law, of course, can be written in a couple of different ways. One of the ways is using the sigma notation. Sigma F is equal to ma, or the sum of the forces is equal to mass times acceleration, or F with a net as a subscript is equal to ma. We'll often be talking about this so frequently in class, we'll just say F equals ma, but we mean it's implied that we're talking about a leftover force. So if I were to solve this problem, and I can clearly see that I'm solving for m here, so I'm going to rearrange the equation solving for the mass of the bike and the rider together. It's going to be the net force divided by the acceleration, or in this problem, 265 newtons divided by the given acceleration of 2.3 meters per second squared. And the mass of the bike and the rider together are going to be 115 kilograms. Notice that the units of mass are kilograms. The units of acceleration are meters per second squared. When you multiply those two things by each other, you get a kilogram meter per second squared. I'll write this in separate units down here on the bottom. So you get a kilogram times a meter over a second squared. That is equivalent. These fundamental units of kilograms, meters, and seconds, these right here, create this derived unit called a newton, a unit of force. That's also something important to see. But as far as this problem is concerned, that's all you needed to know, 115 kilograms. This is problem number 6 on page 98 in the textbook. What average force is required to stop an 1,100 kilogram car in 8 seconds if the car is traveling at 95 kilometers per hour? Let's start with what we know. That's always a good place to start a problem. At least we can write a few things down. The first thing that we know is that the mass of the car is 1,100 kilograms. We know that. We also know that it's traveling at 95 kilometers per hour, so we could say that its initial velocity, or v naught, is equal to 95 kilometers per hour. We should recognize, you kind of should star that and say, hey, wait a second, I'm going to have to convert that to meters per second, and once you deal with that, you should get something along the lines of 26.4 meters per second. We also know that the final velocity of the car is going to be equal to 0 because they basically tell you that you're trying to stop it, and they're asking you to solve for the force. This is a kind of a classic example of you being given kinematics data. Oh, by the way, I did forget that there is additional piece of information given to you that it takes 8 seconds for the car to stop. You should kind of see this information, v final, and time, as kinematics data that would help you to solve for other variables, such as displacement, if you were being asked. Or in this case, more specifically, you could solve for acceleration if you wanted to. You aren't explicitly asked, but it is implied, because in order to solve for a net force, if you're dealing with a net force is equal to ma, you'll see that the only common variable between everything in the world of dynamics, which is basically just this equation, F equals ma, and the world of kinematics, the only thing that is common is acceleration. So you'll see that these two pieces are interchangeable. And that's really a good kind of starting point for this lesson, is recognizing that, hey, acceleration is common to both kinematics, this stuff over here, and dynamics, this world over here. So in order to solve this problem, let's go ahead and put this information over here. I think it helps to make a pictorial model, not required, but if you wanted to, you most certainly could. So I'll make a quick sketch of what's happening. I've got a car, and I know its initial velocity here is going to the right, and at some time, 8 seconds later, we know that its final velocity is equal to 0. In this case, I'm not sure that that helped, but picking a kinematics equation is a logical second step to do. I chose the second equation. V final is equal to V initial plus acceleration times time, knowing that I'm looking for acceleration. Vf minus Vo divided by t is equal to acceleration after I rearrange that equation. Now plugging in these variables, again, I know that 26.4 meters per second is my initial velocity, not my final, so I'm going to get 0 minus 26.4 meters per second divided by 8 seconds is equal to my acceleration. I should recognize that I am going to get a negative acceleration, which makes sense because you can see that I'm initially moving to the right. My velocity initial I indicated was positive. I could have reversed all of these things, but I didn't. So therefore my acceleration is going to be negative. In this problem I get negative 3.3 meters per second squared. The only important thing regarding this vector direction of negative is that the force is also going to be in the same direction as the acceleration. So when I look at F equals ma and say, hey, as this car is slowing down, there must be some leftover force, in this case induced by friction, the tires in the road and the brake pads with the discs and so on. The frictional force is to the left in the direction of acceleration. Therefore, my acceleration is negative. The second part of this problem is basically just the dynamics piece, saying that F net is equal to ma, and then we're solving for that net force. F is equal to its mass. They give you the mass of the car is 1,100 kilograms, times the acceleration, which is going to be negative 3.3 meters per second squared. Kind of ran out of space here. And then finally, my force, the required net force here to do this is going to be negative 3,628 newtons. I am going to have to deal with significance here. I should truncate this down to 2 sig figs, and so I'll get my final net force is going to be negative 3,600 newtons. And I can box that in and call it a day.